This is part 19 in a series of videos in which I'm attempting to repair an HP9830A desktop calculator. In the previous videos I've carried out various repairs and got as far as identifying that a remaining fault was in the ROMs on the main ROM card. And of course I couldn't get the ROMs, so I took the route of designing a replacement ROM card using a standard EEPROM. I've gone as far now as programming the code into the EEPROM. Now if you've been watching the previous videos, then you'll know that the arrangement of the ROM card is fairly unusual in that the ROMs are 512 bytes each, arranged in pairs to give us a 16-bit data word. And that means that the addressing is not just a simple case of taking the address lines and using those to directly address the EEPROM. So what I've had to do is put in place some unusual decoding. So firstly, I've constructed a 16-bit priority encoder, and what that does is it takes the 16 lines that come from the encoded ROM address lines. This is where they select the EEPROM banks in blocks of 512 words rather than 1K words as you'd normally expect. And it takes this and it turns these lines back into a 4-bit binary address. So these constitute address lines 9 up through 12. Also, the lower 8 address lines are inverted. So although they're not really shown inverted here, if you look on the designations for the lines, they're shown as not address 4, not address 5, meaning that they are active low. This is because the lines are configured that way in the actual machine rather than it just being a requirement for the card. So that does mean that I've had to do the same with the card and that the address lines are inverted, but that is taken care of in the adapter I've made here that also inverts them. So when they come out of the programmer, this adapter inverts them, and then they're in the correct sense when they're inverted again for the EEPROM, and that means it will in theory be compatible with the machine. A few of the major differences are the original card needed some odd supply voltages. It needed +5, which is not unusual, but it also needed +16, +12 and -12. It also used quite a bit of power. This would use about 0.7, 0.8 amps at 16 volts. So you're looking at around 10 watts for this card. Now of course the new card is far more efficient, it only uses about half a watt, so that will be an advantage for the machine because it will generate far less heat, so it will keep the machine cooler, and it will also put far less stress on the power supply, so it will be a good thing for the machine in terms of its lifespan. It obviously doesn't look quite as nice, but that is the trade-off when designing new cards for old equipment. Now this card won't fit in of course because it's got the zip socket, so I will make another card. I've ordered several of these boards with the chips soldered direct to the board. But in this video what I want to do is try and read the card. If you have been watching the previous videos, then you'll know that what I did was use this jig to read this card. I then wrote various software utilities that we'll have a look at in a minute to take the raw binary file that comes out of the reader and turn that into a formatted octal file that matched the format in the original HP patent. What I then did was take the dump files from the emulator, and I checked they worked in the emulator. I then wrote a utility to convert the binary file from my failed card into the same dump file configuration that the emulator used, and tried my files in the emulator, and 4 of them don't work. They have various weird problems. So certainly it seems to be the case that the files that came out of my original card don't work. I then wrote a file comparison utility to compare the octal file from the emulator that I'd constructed to the octal file from my card. Did a comparison, and there were a lot of differences all through the file, so there were obviously various failures within the ROM set. So what I'm doing here is I've constructed a single file from the dump files from the emulator. I've converted that into a binary file, a single binary file, and then I've programmed that into the ROM. Bear in mind that the data is actually inverted, so what you see when you read it out, what's actually stored in the ROM is the complement of that, because the data is inverted when it comes out of this card. So once you've taken all that into account, in theory what I should now be able to read out of this new card should be identical to what this should hold. In other words, what I should read out is the data, and that should exactly match the data from the emulator. If I get something different, then I know this card's not working properly. Also, if you recall, the way I have this configured is all the address lines from the programmer are shifted up 2 places. So that is, instead of the address lines on the jig starting at address line 0, 1, 2, 3, etc. on the programmer, they start at address line 2 and run up through 3, 4, 5, etc. upwards. The reason I did that is so that effectively I'm taking 4 readings per memory address, and with the original card that flagged up some errors where all 4 readings for each memory location weren't always the same, and that was indicating that the ROMs had not only failed but also certain other ROMs were very slow to respond. But even if I took the best case data, it didn't match what was in the emulator and didn't match what was in the patent. So hopefully we'll have more luck now reading this card. So the first step is to read the data. I'll turn on the power supply. We'll now read the card, and it's reading it into the programmer. Only takes a few seconds. Okay, so that's read. What I'll do now is process the data in exactly the same way that I did when I took the data from the original card, and then compare that against the code from the emulator, which in theory is what's in here. And if the two match, then we know that this entire setup, including the card, is working the way that it's intended to. So over to the PC, and we'll process the data and see where it takes us. Okay, so we'll take a look at the buffer, see if it contains anything sensible. And as you can see, we have captured something, and if you've been watching these videos, this will probably look familiar. Notice we've got the 4 copies repeated, which is what we expected. As I explained, this is just because of the offset of the address lines, and I want to make sure that we're doing a like-for-like comparison between this card and the old card. Also, I want to make sure that there aren't any speed issues with the new card. So the next thing to do is save this file. Give it a sensible name. Okay, so we've now got this file saved, and what I can now do is open the utility that I used before for converting this hex file into the octal format that we want to compare. So I've opened the utility, we'll select the source file, which is now this one, and we'll give it a sensible name. But I want to invert the data because the data that we got out of the ROM card, if you recall, is inverted. So we need to make sure that we re-invert that to get it back into the format that we want to compare, because that's what was used by the emulator and it's what we obtained this data from in the first place. Also, because we read the entire address space, because obviously the programmer thinks that the card is actually a big EEPROM, we need to limit the number of instructions to the number of instructions that we expect. This will actually be incorrect. I'll come back to this in a few minutes, but what we will do here is create a single, effectively an octal dump file that we can compare against the original. If you watched the previous videos, you know that this process threw up quite a few errors, and these errors here are not errors against the correct source code. They're just checking if all the duplicates when the card was read match each other. And before, we were getting several hundred errors being thrown up because of the errors due to the ROM card speed. So I'll process this file. Notice now we're getting 0 errors. That's a good start. And what we should end up with is the data in an octal format, but with the data inverted, which is exactly what we're getting. This is the file we've just created. Now, I said the size is incorrect. Now, at the moment, I don't have the N part of the file in place. You notice here it's saying 0. And that is something I need to resolve. It's just because of the way I constructed the original file. But I will come back and resolve that before I try the card in the machine. I just want to see if the data across all the banks is correct. So the next step is to copy this file into our file comparison directory, and that way I can run the file compare and compare it against the original emulator dump file, and in theory the two should match apart from the N part. So I'll just copy this, and what I'll do now is run the file comparison utility. So we'll select the two files. So we've got the dump file from the emulator, and we've got the one that we have just created. And this utility will run the two. Now, we will get errors at the end of the file, but we were getting errors all the way through previously, and so we shouldn't see any errors until we're getting fairly close to the end of the files. Okay, so as I said, that's to be expected. It's just because the dump file that I've constructed, I haven't included the last EEPROM image. And again, that was intentional as a sanity check to make sure that as I go through all this, I'm picking up errors only in the correct place. But if we do the comparison again, you'll see that for the bulk of the comparison, there are 0 errors. In other words, we're looking all the way through the file up to the end, and until we get to the end where we expect to see errors, there aren't any. And as I say, that's a good sign. It means that we are essentially getting exactly what we're expecting. If we go back to the programmer, and one of the main issues, of course, with a card like this, because of the odd decoding, is making errors in the decoding logic. Okay, if we go back to the buffer, you may recall from previous videos that there were certain key values I was looking at. One of the issues with this card is the odd address decoding. So it is important that I check that it can properly decode all the way through the various blocks of EEPROM, because it is odd the way that that decoding is done. It looks good so far because we haven't seen any errors when the output file is compared against the file that was used to generate the code for the ROM. But just as a kind of sanity check, I just want to check a few key addresses. The first one is the first address, of course, but bear in mind that we have 4 readings in this buffer per address, so we need to multiply the addresses we're looking at by 4. Now the next key address was 815 hex, so if we multiply that by 4, we need to look at 254 hex. So if I run up to 254, we'll see that the value here is B4E3, and that's correct. If you want to know why that's correct, just look at the previous videos, but there are certain key addresses that I've made notes of, just to make sure there's no skew in the data and that it's the bank switching is all correct. I'll go through and check the rest of these off camera, but as I said, the file comparison seems to be correct, so I don't think there'll be any errors. Okay, that's it for this video. In the next video I will be plugging the card into the machine and seeing if it works, or if we need to implement some additional decoding. As ever, any comments or advice is welcome.